Hello everyone. In today's class, we are going to discuss new chapter current electricity. So in this chapter, first of all, we will discuss about electric current. Correct? So what is electric current? The flow of charge per unit time to the given area is what is electric current. So according to definition of electric current, flow of charge per unit time to the given area is what is electric current. Let's suppose we have one wire. All right. And this is the cross section of the wire. And the cross section area is, let's suppose, capital A, and these electrons are passing from this cross section area, correct, in the unit time, correct. So total charge flow per unit time through this given area is what? It is the electric current. Let's suppose in the t time, total q charge is passing from this A area, correct. Total q charge is passing in t time through this area. So what is the electric current, correct? So the electric current can be written as what? It is the q by t. Total charge, how much is passing from this cross section area in t time? It is q, and time required to charge passing from this cross section area is t here. So q by t is what? It is the current, correct. If we will talk about the unit, SI unit, so we know that SI unit of the charge is what? Is the coulomb, and time is second. So coulomb per second is what? It is the SI unit of the current, otherwise ampere. All right. So ampere as well as coulomb per second, both are SI unit. Keep this thing in your mind, everyone. All right. So note down. Now next we will discuss about the average electric current and instantaneous electric current. So in the average electric current, interval of time is very large. But if we will talk about the instantaneous electric current, so in the instantaneous electric current, interval of time is very, very small. It is infinitesimally small. This thing already we know from the kinematics chapter, correct? So what is the basic difference between the average and instantaneous? In the average, interval of time is very large, but when we are talking about the instantaneous electric current, so here interval of time is very, very small. Here del t, here what we are writing, I equal to limit del t tend to 0, means here time is approaching to the 0. Limit del t tend to 0 meaning is what? Correct? Del t is approaching to the 0, but it is not equal to 0. Correct? Means here del t can be 0.00001, but it is not equal to 0. Alright, so here we are finding flow of charge in very, very small time. Correct? And the ratio of these both things is what? It is the instantaneous electric current, dq by dt. Here d is representing very, very small, and del is representing very large. Alright? So this is the basic difference between the average and instantaneous electric current. So I hope this thing is clear to everyone. Note down this both the formula, and then we will discuss some numerical. Then we will get some clarity how we can find out average and instantaneous electric current when we have numerical. Let's see one question on the basis of this concept. Find the current at t equal to 2 seconds given that the charge q equal to tq plus 2. So here charge as a function of time we have in this question, and current we want exactly at 2 seconds. So here we want instantaneous current, because here in this question he is asking what is the current at t equal to 2 seconds. So exactly at 2 seconds we want, means here we have required instantaneous current. So let's see how we can do it this question, everyone. We know that instantaneous current can be written as dq by dt, correct? When we are finding instantaneous current, that interval of time is very, very small. This thing we knows already. So charge as a function of time we have. So we will find first of all current as a function of time. So we need to differentiate here. And what is the value of q? It is tq plus 2. So do it differentiation. Differentiation of tq is 3t square, and differentiation of 2 is 0 because 2 is constant. So current as a function of time we are getting 3t square. Now what we will do it, we will put here t equal to 2. So now we need to put here t equal to 2. So if you will put here t equal to 2, now what we are getting here after simplification, the square of 2 is what? It is the 4. 4 into 3 is what? It is 12. So exactly at t equal to 2 seconds, how much current is flowing from this wire? It is 4. It is 12 ampere. So this is the correct answer for this question. So I hope this thing is clear. Note down everyone. Let's see next question. Find the average current between t equal to 0 and t equal to 2 seconds, given that the charge equal to tq plus 2. So here we want average current. All right, we're looking for the average current here in interval t equal to 0 and t equal to 2 seconds. All right, so average current can be written as what? It is del q by del t. And del q can be written as what? It is q final minus q initial divided by del t. Okay, so what is the q final? Q final is the charge at t equal to 2 seconds. So here we will put t equal to 2 seconds in this equation. So t we will replace with the 2. So it is 2q plus 2. So now it is how much? Cube of 2 is 8. 8 plus 2 is 10. 10 coulomb. Q initial means at t equal to 0 second. So t equal to 0 plus 2 means it is 2 coulomb. Okay. Now we got it Q final and Q initial both. So I average can be written as what? I average is equal to del Q by del T. So final minus initial means 10 minus 2 divided by interval of time. 2 minus 0 means it is 2. 10 minus 2 is 8. 8 divided by 2 is 4. 4 ampere is the answer. So the average current in between 0 to 2 seconds is how much? It is 4 ampere. This is the final answer for this question. So I hope this thing is clear, everyone. Note down. Let's see next question. Current is given as I equal to t power 4 plus 1. Find the charge flow till t equal to 5 seconds. So in this question we want how much charge is flowing till 5 seconds, correct? So let's see how we can do it this question, everyone. So here we have I equal to t power 4 plus 1, correct? So we know that this I can be written as dq by dt. Now dt we are putting on this side. So we have now correct this thing we have. All right, so now we need to integrate here because we want charge till 5 seconds. So we are integrating on both sides. And what should be the limit of integration? Think it, everyone. What should be the limit of integration? Here we want charge flow till 5 seconds, means 0 to 5. This is the limit of integration, 0 to 5. Now integration of dq is what? It is q. Integration of t power 4 can be just t power 5 divided by 5. Put limits 0 to 5 plus integration of 1 is t. So this is t 5 0. Upper limit is 5, lower limit is 0. Now put upper limit minus lower limit. When I will put lower limit 0, then it is 0. It is getting 0, correct? So first of all I am putting upper limit, so it is 5 power 5 divided by 5 minus lower limit. So when I will put here t equal to 0, then it is getting 0. Now plus here we have t and the power is here limit is 0 to 5. Put upper limit minus lower limit. So 5 minus 0, correct? So now only we have 5 when we are putting the limits here. So q equal to 5 power 5 divided by 5, so it is 5 power 4 plus 5. So how much we are getting here after simplification? 5 power 4 is 625 plus 5, it is 630. So finally we have 630 coulomb. This is the correct answer for this question. So I hope this thing is clear to everyone. Note down. Now let's see next topic. Is current a scalar or a vector quantity? So now the question is, current is a scalar quantity or it is vector quantity? This thing we want to determine. So if we will see it current, so current has magnitude as well as it has direction also. This thing we know. Let's suppose we have one wire and from this wire I current is flowing. We know that current is always flowing from higher potential to lower potential. This thing we know, correct? Means current has some specific direction because it is always flowing from higher to lower potential. That's why current has some specific direction. All right. And current has magnitude also. But if any quantity is vector quantity, then that quantity should has magnitude, direction, as well as it should follow vector's laws also. Then only we can say that this quantity is the vector quantity. Correct? So now we will check here current is following vector law or not. All right. So let's suppose here we have two wire. In the first wire, let's suppose 1 ampere current is flowing, and in the second wire 2 ampere current is flowing. So what should be the total current in this wire? It should be 3 ampere. Correct? And how we will determine this current? With the help of Kirchhoff current law. So if we will use here Kirchhoff current law, so we will get current in this wire. It is 3 ampere. All right. So resultant current in this wire is not depending on the angle. Correct? If the angle between this two wire is 30 degree, 40 degree, 50 degree, answer will remain the same. Correct? But this thing will not happen with the force. If we will look force, let's suppose here we have one block in this direction, F1 force is acting, and in this direction we have F2 force, and let's suppose angle between these two forces theta. So what is the resultant force on this block? So according to parallelogram law of addition, we know that resultant force can be written as F1 square plus F2 square plus 2F1 F2 cos theta. And what is the theta here? Theta is the angle between this F1 and F2. All right. Means resultant force is depending on the angle because force is the vector quantity. Correct. So resultant of this two vector quantity is depending on the angle between the two vector. But this thing is not happening in the current case. It is not depending on the angle. That's why it is not following vector's law. All right. So current is not following vector's law. That's why it is the scalar quantity. Correct. Current is what? It is the scalar quantity. It is not a vector quantity. But if suppose we have three options, vector, scalar or tensor, then which one is correct? So the correct answer will be tensor. Tensor is most accurate answer. Why tensor is more accurate answer? Because if the quantity has magnitude as well as direction, but it is not following the vector's laws, then that type of quantity is known as the tensor quantity. Same thing is happening with the current also. Correct? That's why current is what? It is the tensor quantity. But if we have only two choices, vector, scalar, then we will take on the scalar. All right. So I hope this thing is clear why this current is a scalar quantity and why we are saying current is the tensor quantity. All right. Note down everyone. Let's see next topic, electric current density. So what is the definition of electric current density? The electric current density is defined as the amount of electric current flowing or passing through a unit cross-sectional area, and it is vector quantity. So how much current is passing from unit cross-sectional area? This thing we will define with the help of electric current density. All right. And what is the mathematical formula of electric current density? It is I by A. Correct? Ratio of I by A is equal to what? It is the current density. And if you will write this current density in the vector form, so it is I equal to J dot A. All right. And direction of current and direction of current density in same direction. Correct? Keep this thing in your mind. If the charge is flowing in the wire, if the positive charge is flowing in the wire from north to south, so direction of the current should be what? It should be north to south. This thing we know that. Correct? In the same direction, we have current density also. All right. So now let's see one example, everyone. let's suppose here we have one wire, and the cross section area of this wire is varying, it is not same. So here we have one wire, and the cross section area of this wire is varying continuously. Let's suppose area of the section is A1 and the area of the section is A2, and current flowing from this wire is, let's suppose, I. All right. So current passing from A1 section and the current passing from A2 section should be same. This thing we know that. Here cross section area is varying, but the current should be same. All right. If I will write current density at the section 1, so it is what? It is J1 equal to I by A1. And if I will write current density at section 2, so it can be written as J2 equal to I by A2. This thing we know and clearly visible, A1 is greater than to A2. If A1 is greater than to A2, so if A1 is greater, definitely J1 should be less. And here A2 is greater, A2 is less, so J2 should be greater. All right, because inverse relation is present between the area and the current density. If area is large, then density will be less, correct? So A1 is large, so current density should be less, means J1 should be less than to J2. This relation we are getting. All right. So I hope this thing is clear to everyone. What is the electric current density, correct? And electric current density is the vector quantity. What is the mathematical formula, correct? What is the relation between current, area, and the density? So this all things is clear to us. All right. So note down everyone. Now let's see next topic, drift velocity. So what is the definition of drift velocity? The average velocity attained by the charged particle in a material due to the electric field. So when electric field is present, so charged particle is getting some average velocity, and this average velocity is known as drift velocity, correct? So let's see what is happening in the wire. Let's suppose here we have one conductor. This is conductor, everyone. And right now it is not present with the battery. So if it is not present, if it is not connected with the battery, so definitely inside the wire electric field is not present. Okay. And inside this conductor we have some free electron also. So this is the free electron. So this free electron is moving from here to here. So let's suppose here the proton is present. So collision is happening between the proton and the electron. Now it is moving here. So again here collision is happening. So now it is going like this, and here collision is happening, then it is going here. So in this case, what is happening? In this case, net displacement is zero. You can see it here. Here we are not getting net displacement. Correct? So net displacement is zero. So definitely drift is zero here. So when wire is not connected with the electric field, then here we are not getting any displacement. Net displacement we are getting zero. Correct? Because initial and final position is same here. That's why it is happening. Alright, so in the first case, without electric field. Correct? And in the second case, what is happening? Electric field is present, so it is with electric field. Okay, so when electric field is present, then what is happening? Then some force is acting on the electron. Let's suppose initially this free electron is present here. So on this electron, electrostatic force is acting in this direction, and it is E. Correct? So in this direction, electrostatic force is acting. So due to this electrostatic force, it is moving in the forward direction. And let's suppose here proton is present. That's why here collision is happening between the electron and proton. It is changing its paths. But right now, what is happening in the forward direction? Some electrostatic force is acting. Due to this, it is traveling some extra distance. When electrostatic force is not present, then it is traveling less distance. But when it is present, then it is traveling extra distance. So now it is here, and now again it is moving the forward action, so it will travel some extra distance. It is here, and then here collision is happening. All right, so electrostatic force is acting in this direction. This is the direction of electrostatic force. Correct. So when it is going in backward action, so it is decelerating. Correct. And when it is moving the forward action, then it is accelerating. So when it is moving in forward action, then it is accelerating. That's why it is traveling extra distance. And when it is going backward, then it is decelerating. That's why it is traveling less distance. So due to this, what is happening? We are getting net displacement, and this net displacement is known as drift here. Correct, everyone? So I hope this thing is clear why we are getting net displacement when electric field is present. All right. So here this net displacement is very small. That's why drift velocity is very small as compared to actual velocity of the free electron. Actual velocity of the free electron is approximately equal to 3 into 10 raised to 8 meter per second. Correct? This is the actual velocity of the free electron, and it is very less as compared to, and drift velocity is very less as compared to free electron velocity. Is it clear to everyone? What is the drift velocity? What is the drift? Why we are getting this drift? All right, note down. Now let's see next topic, drift velocity and current. So now we will find relation between drift velocity and the current. So let's see it, everyone. Let's suppose we have one wire, and the cross section area of the wire is, let's suppose, A. Correct? And let's suppose drift is dx here. And what is the drift? This thing already we knows. Correct? And why we are getting drift? That's all things we knows. And inside this wire we have some free electron also. So these all are free electrons. Let's suppose volume of this dx region is V. Correct? So if I will write here V, this volume, so it can be written as A into dx. Correct, everyone? So volume of this region is what? It is AdX. Volume of this drift region is what? It is AdX. All right. Now we know that one thing, charge density can be written as number of charge per unit volume. This is the charge density. So small n is representing charge density. So here number of charge present in this region, in the drift region, can be written as what? N into V. And V already we have, it is AdX. Correct? So number of charge present in this region is NAdX, and the total charge present in this region can be written as what? dq equal to Ne. Charge present on one electron is E, so if I will multiply N with the E, so we will get total charge present in this region. All right. Now the next thing is what here? We will put here value of N. It is N A dx into E. This thing we are getting finally. And we know that dq by dt is what? dq by dt is the current. So now divide this thing with the time. Correct? So dx by dt is what? It is the velocity, and dq by dt is the current. So now we are getting finally I equal to NEA Vd, because dx by dt is what? It is the drift velocity. So now here we have one very important relation, I equal to NEA Vd. So I hope this thing is clear to everyone, how we will get relation between current and drift velocity. Note down, everyone. Let's see one question on the basis of this concept. A current of 10 ampere exists in the wire of cross section area 5 mm square with drift velocity 2 into 10 raised to minus 3 meter per second. The number of free electron in each cubic meter of the wire. तो इस क्वेश्चन में हमें स्मॉल n फाइंड आउट करना है, चार्ज डेंसिटी हमें फाइंड आउट करनी है. तो करंट हमें गिवन है, करेक्ट, क्रॉस सेक्शन एरिया में गिवन है, और ड्रिफ्ट वेलोसिटी गिवन है. तो हमारे पास में एक रिलेशन है, अभी अभी हमने पढ़ा था, I इक्वल टू NEA VD. ये रिलेशन हमें पता है, करेक्ट. तो यहाँ पर स्मॉल n फाइंड आउट करना है, तो n इक्वल टू हम लोग लिख सकते हैं I बाय NE लिख सकते हैं हम लोग ई ए वी डी। सो आई बाई ई ए वी डी लिखा जा सकता है एन इक्वल टू, अब सारी वैल्यूज पुट करते हैं। आई कितना है 10 एम्पियर, ई कितना है 1.6 इंटू 10⁻⁻90, क्रॉस सेक्शन एरिया कितना है 5 mm² मीन्स 5 इंटू 10⁻⁻6, और ड्रिफ्ट वेलोसिटी है यहाँ पर 2 इंटू 10⁻⁻3, करेक्ट। तो 5 इंटू 2 करोगे तो 10 हो जाएगा, तो इससे ये कैंसिल आउट हो जाएगा, एंड 1 डिवाइडेड बाई 1.6 करोगे देन इट इज 0.625 एंड -28। अब इसे सिंप्लीफाई करने के बाद में जो फाइनली आंसर आएगा वो 625 इंटू 10⁻25 हो जाएगा, करेक्ट। और अगर आप ऑप्शन चेक करो तो आपको ऑप्शन बी मिलेगा यहाँ पर, तो बी इज द करेक्ट आंसर फॉर दिस क्वेश्चन। सो आई होप आपको क्लियर हुआ होगा इस क्वेश्चन को हम लोग कैसे सॉल्व कर सकते हैं और क्या आंसर होना चाहिए। नोट करो, फिर आगे बढ़ते हैं। Let's see next topic, mean free path and relaxation time. So what is the mean free path? Mean free path we are representing with the lambda, and it is average distance between two successive collision, correct? So let's suppose here we have one conductor, correct? Here we have one conductor and this is the electron. So this electron is moving from here to here, then here is no collision, correct? And collision is happening at this place. Here let's suppose proton is present, so between this electron and proton here is collision, correct? And then it is going here, and here collision is happening, then it is going here, and then it will move here. So from here to here it is free, so it is lambda 1, then it is again free lambda 2, then it is lambda 3, and this is lambda n. Let's suppose this is lambda n. Now take average of this all free path, correct? Add this lambda 1, lambda 2, lambda 3, lambda n, and divide by the n. So you will get mean free path, correct? Now the next is relaxation time. So average time between two successive collision is what? It is a relaxation time, and we are representing with the tau. So from here to here collision is not happening and this electron is in relaxed condition, that's why we are saying it is a relaxation time. So, and it is tau 1. Then here to here it is again relaxed and it is tau 2 time, then it is tau 3, and this is tau n. Now take average of this all, correct? If you will take the average of this all, then you will get relaxation time, and this is the formula. If you want to calculate relaxation time, then use this formula. All right, note down. Now next we will discuss about the drift velocity. So about the drift velocity already we know, and we have one relation also, I equal to NEAVD, correct? Where VD is what? It is the drift velocity and I is the current. So this relation already we know. Now we have one more relation for the drift velocity, and it is important. Drift velocity can be written as acceleration of the electron into relaxation time. And acceleration of the electron can be written as what? This thing also we know. It is EE by mass of the electron into tau, correct? So this relation is important for us. We need to keep this relation in our mind. Note down, everyone. Now let's see next topic, mobility. So what is the definition of mobility? Mobility refers to how easily a charged particle such as an electron or ion move through a material when subjected to an external electric field, correct? So what is the formula here according to the definition? It is the drift velocity by electric field. Keep this formula in your mind, correct? Now see it one example, then you will get clarity about this mobility. All right, so let's suppose we have one electron and one proton we have, and we know that mass of the electron is very less as compared to the mass of the proton. This thing we know, correct? And this electron and proton we are putting in same electric field, and we know that charge present on the electron and proton is same. This thing we know, correct? All right, we know one more thing, drift velocity can be written as acceleration into tau, correct? And acceleration can be written as EE by Here electric field is same for both the charged particle. We are putting this electron and proton in same electric field, and mass is different, correct? So drift velocity can be written as EE by m into tau. Okay. Now we are putting this drift velocity here in this formula. So EE by m into tau divided by electric field, correct? So now the next thing is what? Here EE will get cancelled out. So mu equal to, we will get E tau by m, correct? This thing we are getting. So we can see it here, one thing, this mobility is inversely proportional to mass, correct? Means if mass is greater, then mobility will be the less. And we know that mass of the electron is very less as compared to the mass of the proton. So definitely mobility of the electron is very high as compared to the mass of mobility of the proton. All right. Means if mass is less, then definitely it can move easily. If someone has less mass, then it can move easily. If the mass is heavy, then what will happen? It will feel difficulty when it is moving in the electric field. Same thing is happening with the electron and proton also. All right. So I think right now it is clear to everyone what is the mobility. All right. Note down everyone. Now let's see next topic, Ohm's law. What is the statement of Ohm's law? The potential difference across conductor is directly proportional to the current as long as temperature and other physical factor remain the constant. All right. So let's suppose we have one conductor and connect this conductor with one battery. And connect one emitter also. And the potential difference of the battery is V. All right. Let's suppose I current is flowing in the circuit. Now what we are doing here, we are increasing potential. So what we can see it here, if I am increasing potential, then current is also increasing, and it is increasing linearly. All right. This thing we will find in the circuit. But temperature and other physical factor remain the constant. Other physical factor means length, width, diameter. This all should be same, correct? And temperature also should not be changed. Then what we will get, V is directly proportional to I. Now remove the proportionality sign, then you will get one constant, and this constant is known as R, means resistance. And this is our Ohm's law. And if you will plot voltage versus current graph, so if I will plot voltage versus current graph, so we will get linear graph here. Let's suppose initially voltage is 1 volt and current is 1 ampere. Now voltage is 2 volt, then current will become 2 ampere, then 3 volt, 3 ampere. This thing you will get, correct? Means linearly it will increase. Reading can be different also. All right, reading can be different, but relation will be linear here. So keep this thing in your mind. So linear graph we will get. All right. Note down everyone. Now let's see it one question. In the given figure, a battery of EMF E is connected across the conductor PQ of length L and different area of cross section having radii R1 and R2. R2 is less than R1. So here we have one circuit and we have this type of conductor. This type of conductor is given in this picture. And now we are connecting this conductor with the battery. So what is happening if I will draw the electric field lines? This is the field lines. Correct? So what we can see it here. If you will see it here, when I am drawing the electric field, correct? Electric field is increasing here. Why? Because at this cross section, separation between the field line is more here. But when I am moving P to Q, so in this direction, separation between the field line is continuously decreasing. That's why we can say that electric field is increasing here. Correct? This thing we know from first chapter, electrostatics. All right. So electric field is increasing. This thing is clear to us. Now see it options here. So choose the correct option as one move from P to Q. So when we will move from P to Q, drift velocity of electron increases, and we want here correct options. So drift velocity of electron increases. So see it, what will happen with the drift velocity. So we know that one relation Vd equal to EE by m into tau, where E is what? It is the electric field. So we can say that drift velocity is directly proportional to electric field, correct? And continuously what is happening, electric field is increasing when we are moving from P to Q. So definitely drift velocity will also increase here. Means option number 1 is correct. Now see second option, electric field decreases. We know that electric field is increasing here when we are moving from P to Q. And here in the second option is given electric field decreasing. So this is wrong. Now the next is electron current decreases. We know that current in the conductor is constant, correct? If it is uniform or non-uniform wire, current will remain the same. So this is again wrong. So correct answer is only option number 1. So I hope this thing is clear to everyone. All right, note down. Now let's see next topic, vector form of Ohm's law. So let's see how we will get vector form of Ohm's law. We know I equal to NEA VD, correct? This relation we knows. And we knows one more relation, drift velocity can be written as Vd equal to EE m into tau. This is equation number 2, correct? So what I am doing here, I am putting this Vd value in equation number 1. So what I will get, I equal to NEA EE by m into tau. This thing we will get, correct? So I equal to NE square E m and tau I am putting in multiply into area. So NE square tau A by m into E. This thing we are getting, correct? Now do it one thing, multiply with the length of the conductor and divide with the length of the conductor. Do it this thing. So I am multiplying length and divide with the length. And we know one thing, if I multiply electric field with the length, then it is equal to the potential difference across the conductor. This thing we know from the second chapter. So now we have NE square tau A by ml into V. Now simplify this, so we will get V equal to ml by NE square tau A into Y. This thing we are getting, correct? Now compare this relation with the Ohm's law. We know Ohm's law can be written as what? V equal to Ri. So if I will compare, so with this I we have ml by NE square tau A. So resistance we got it here, ml by NE square tau into A. This is the resistance formula, correct? This is resistance. All right. So resistance we got it. Now we know one more thing. Resistance can be written as rho L by A also, correct? So with this L and A we have m by N E square tau. This thing we have. So m by N E square tau we have, correct? M by N E square tau. So this is what? This is the resistivity. So if I will compare this relation with this formula with this rho L by A, so resistivity we are getting. Now we have resistivity formula. It is m by N square tau, correct? We knows one more thing. Conductivity is reciprocal of the resistivity. So what we are getting here? Conductivity. This is conductivity. All right. So we are getting Ne squared tau by m. So now we have conductivity also. Okay. See this equation number third. Let's suppose this is equation number third. So from the equation number third, what we are getting? Actually, what we want Ohm's law in the vector form, correct? So now let's see this equation number third. So from equation third, what we will write here, from equation third. See it, what we have, I equal to NE by m into tau. So can I write like this? I by A equal to Ne square, correct? Ne square E by m into tau. Can I write like this? Think it. And this I by A is what? It is the current density, J, correct? And Ne square into tau by m is what? It is the conductivity. So J equal to sigma E we are getting. J equal to sigma E, correct? And J is what? It is the conductivity. So here, because we want Ohm's law in the vector form, so J is what? It is the current density and it is vector quantity. So it can be written as J vector equal to sigma E vector. So now we have Ohm's law in vector form, correct? J equal to sigma E. This is vector form of Ohm's law. And if I will write Ohm's law in scalar form, so it is V equal to Ri. So this is scalar form and this is the vector form. All right. So here we have so many formula, like what is the conductivity formula, correct? We have resistivity formula, we have resistance formula. So remember this all. Now let's see next slide. Conductance and conductivity. About the conductivity already we know that, correct? About the resistance also we know. So conductance is what? It is the reciprocal of the resistance. So G equal to what? It is 1 by R. And what is the unit of the conductance? It is mho. And this is a symbol of the conductance, correct? Now conductivity is what? It is a reciprocal of the resistivity. SI unit is mho per meter, correct? Mho per meter. This is the unit of conductivity. All right, everyone, note down.